Welcome to our discussion on maximum and minimum values. These are some of the most important applications of differential calculus. We often are trying to optimize things, find maximum and minimum values of a function over a particular interval. So these techniques do become highly important, especially in econ. You can see from the graph here that it obtains a maximum value when x equals 3, and that value is, well, 6, right? Well, actually 5, sorry. And then here at x equals 6, we get a minimum value of -2. Now, these are sometimes considered a global max and min or an absolute max and min. It's just two different names for the same thing. So when you hear people refer to absolute maximums or global maximums, they're just referring to the value that is the highest, right, or lowest, if we're talking about minimum, that the function takes on over an entire interval, which is why they're also considered extreme values. Figure 2 shows a graph with absolute maximum at D, right? You can see how it takes on its highest value here. Absolute minimum over here at A, that's the lowest it takes. But you'll also notice that if we look at just this little neighborhood, this smaller interval from A to C, that it takes on a maximum value here at B. And in fact, if we look at the interval from, let's say, B to D, it takes on a minimum at C. And likewise, if we look at the interval from, let's say, D to over here somewhere, it takes on a minimum at E. So you can have what are called local max and mins, which are just maximums and minimums in a smaller interval, in a smaller neighborhood. So when you're talking about over some interval around a point, that point just has to be the highest one in that entire neighborhood, or the lowest one, or the highest one. You can see this is still considered a local max, right, on a smaller neighborhood, but it also ends up being a global max as well. So we have the difference between global, right, or absolute max and mins, and then local min and maxes, which just mean it's the same thing. It's a min and a max, but on a smaller interval, right, in some small little neighborhood around that point C. Here's another illustration to show the point, right? X equals 4 is a local minimum. X equals 12 is a local minimum, but it's also the absolute minimum. X equals 8, right, point J, is a local max, and then the absolute max happens over here, looks like close to 1. So an absolute max and min doesn't necessarily have to be at one of these kind of hills and valleys. It can be at the end of the interval. Another example of something that takes on local mins and maxes that are, in this case, also happen to be absolute mins and maxes is our friend cosine, right? And then of course sine is going to be the same way. Those two functions oscillate back and forth, having maximum values of 1 and -1 infinitely many times, so it's going to have basically an infinite number of both local and absolute maxes and mins. Which brings us to the extreme value theorem. If f is a continuous function on some closed interval, and that's important, it has to be closed, a to b, so you'll notice the square brackets, then this function f obtains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in that interval, and those numbers can be the endpoints, right? So those numbers can be a and b. And the three graphs below show examples of this. We can see that here's our absolute max, here's our absolute min, here's our absolute max, here's our absolute min that happens to be an endpoint, right? Here's an absolute max, this looks like that might be the same, right? And here's an absolute min. Here are some examples where it doesn't seem to work. This function has an absolute minimum here, but it has no absolute maximum because of the open circle, right? It doesn't actually attain that maximum value of 3. It gets really, really close to it. And then this one has no absolute min because of the open, and no absolute max either. You could kind of say that there might be a dot there, but there isn't, right? That implies that it just keeps going. So that function just keeps getting taller and taller. Now this doesn't contradict the extreme value theorem for a couple really important things. This function isn't continuous, so that's why it doesn't contradict the extreme value theorem, because the extreme value theorem says the function has to be continuous. This function isn't on a closed interval, it's on an open interval, right? So those two parts of the extreme value theorem are very important. It has to be a continuous function, has to be on a closed interval. Otherwise, you can get these type of oddball examples that contradict the theorem. All right. The extreme value theorem says that a continuous function on a closed interval has a max and a minimum value, but it doesn't tell you where those values exist. We do have some techniques to help us find them, but for now the extreme value theorem just tells us that they're there, doesn't tell us where they are. But from examination, for instance, of this picture, you can see that the max and min both seem to have a tangent that is horizontal, which leads us to Fermat's theorem. And it says if your function f has a local maximum or a minimum at some point c, and if the derivative exists at c, right, so the function is differentiable at that point c, then we know the derivative has to equal 0. Please pay attention to the fact that this theorem doesn't go in both directions. It doesn't say that if the derivative equals 0, it must be a local max and min. It says if we have a local max and min, then the derivative must equal 0 if it even exists at that point. So that's a key thing. It helps us, again, to find those maximum and minimums, but it doesn't guarantee. So just by taking a derivative and setting it equal to 0 doesn't guarantee we have a min and a max. It just means that it's possible. Here's an example. If you take the derivative of that function, set it equal to 0, you get that it equals 0 at 0. But quite plainly, from the picture, that is neither a minimum nor a maximum. Okay, so just because the derivative equals 0 doesn't guarantee we have a min and a max. And that's what I mean here, is that Fermat's theorem is not an if and only if. It does not go in both directions. Here's another example where we have a minimum value at 0, but the derivative doesn't even exist. Now luckily for us, most of our examples we're going to be dealing with are going to be smoother curves where the derivatives will exist everywhere. But this is just one of those, again, kind of special examples that shows these things can break down if you don't follow all of the rules of the theorems. So we must be very careful when trying to apply Fermat's theorem. First of all, we must know that even when the derivative equals 0, that doesn't necessarily mean we have a max or min, as we saw from example 5. And we also know that we can get an extreme value where derivatives don't exist. So we can't just go around taking derivatives and setting it equal to 0 and then saying those are our only possibilities. We have to also look for places where the derivative doesn't exist. Okay, but so you might be thinking, well, then this Fermat's theorem is just crap, it doesn't help me. Well, it actually does. And it does suggest a lot of things. It at least tells us where we can start looking for these extreme values, right? We know that a critical number of a function f is a number c in the domain of this function f, such that either the derivative at c equals 0 or the derivative doesn't exist. So there we go. We've narrowed it down. We've got a function. It's continuous on an interval, on a closed interval, right? We're trying to find maxes and mins. We know that we only have to check where the derivative equals 0 and where the derivative doesn't exist. And those are the only possible places where we can find these critical numbers, these mins and maxes. Because if the function has a local min or max, then it has to be at a critical number. And this leads us to what's called the closed interval method, and it's just a fancy way of saying go find some max and mins, right? If you have a function that is continuous on a closed interval and we're trying to find mins and maxes, it's very simple. All you have to do is take the derivative, set it equal to 0, and then evaluate it at those points. Find any points where the derivative doesn't exist, evaluate it at those points, and then check the endpoints, right? Because remember, we're on a closed interval, so you have to check the endpoints because the function could end at a high value or end at a low value or start right at either of the two. So that's all you got to do. Check the endpoints, check the derivatives, check the points of discontinuity, and whichever one of those, and by checking, right, we're taking those x values, plugging them into the function, and calculating the corresponding y values into the function, not the derivatives, into the function. And when you check all those, you're just looking for which one is the biggest and which one's the smallest. And that's it. That's how we're going to test for max and min values.